Okay, hello everybody. Welcome to the next installment of our weekly reading groups. This week I'm very excited to welcome Saleh Ashkboos. He is a third-year PhD student in computer science at the Computer Science Department of ETH Zurich. He's advised by Professor Torsten, Hoefler, and Professor Dan Alistar. I think I said that right. His research is on accelerating deep neural network training. He's also working on developing systems and algorithms for large-scale graph processing, and he's an associated doctoral student of the ETH AI Center. Before ETH, he got his master's in computer science from Sharif University of Technology under Amir Danishgar. He's here today to present his recent work on SliceGPT, which was accepted at ICLR 24, which is work he did during an internship at Microsoft. So it's really great to have you with us today. The stage is yours.
Okay, thank you. Thanks for inviting me. It is quite interesting to talk with many with many researchers and engineers in this field. So let me share my screen and start. Can you see my screen?
Yeah, we can. Yes.
Okay, perfect. So basically, because I cannot see the chat right now, so it would be nice if you have any question, then you just
I'll let you know.
Stop me, open your microphone and just ask whenever you want. Of course, I have some checkpoints and some points that I stop and try to ask everyone if they have any questions, but feel free to ask whenever you want. So basically, this is our recent work about compressing these LLMs. So it's called SliceGPT. This work is done during my internship with Microsoft and Microsoft Research in Cambridge. Okay, so let's get into it. Okay, so first of all, let's start with some introductory slides. So basically, so we know all how these large language models, how important are these models. But one thing that we all agreed on is that these models are really large. And this means that if you think about the number of parameters, the path that we came through the last 5 or 6 years, we started from something like a few million parameters to something like few 100 billion parameters today. And then basically, if you want to think about one of them, which I think was the most popular one for a long time, is GPT-3 with 175 billion parameter. If you want to think how big is this, then you can think about storing this model needs about 700 gigabytes. If you store every single parameter in FP32 in a standard floating point, or 350 gigabytes if you store it in FP16. So basically, this means that if you are given a pre-trained model and you don't want to do any retraining and you just want to give a set of tokens and just ask your model to do the inference, then you need to from 5 to 9 A180 gigabyte of the memory. And or if you are using some consumer type GPUs, which is a bit weaker, but most people use them, then you need something like 15 or 30 based on the precision that you are running of this RTX 3090. So this is a huge amount of computational resource that you need to only run the inference, the forward pass of this model. And this shows that, okay, one of the most important challenge here is that basically these models needs they use a high amount of memory. The other part is that apart from the memory, if you think about this model, so this is you can find a standard transformer block, one transformer block with attention and layer norm and the MLP. So if you think about these different modules in this model, then you can find that most of the computation will be done in the matrix multiplication form, And the matrix multiplication is at the core of these models. So you have this matrix multiplication with different name, Q, K, V, out project. So these are linear layer, which is essentially matrix multiplication. And then if you think about, again, for this GPT-3 model, then you need to do 750 teraflops for doing a single inference for very, very small, I would say, number of tokens, with 2K tokens. And you can break down these flops in different linear layers, and you see that, okay, most of this computation will be done in this matrix multiplication. So the second challenge would be these LLMs, apart from the memory usage that they have, they are super expensive to run because they need a huge amount of flops because of the large matrix multiplication, this linear layer that we have everywhere. Okay, but if you are familiar with the field of this high performance computing, these kind of things, these are the challenge that we have them for a decade in the high performance computing. And there are a lot of solutions that people have developed and used in the other fields. One is the quantization, which is actually, so you have a vector of the elements, and then you just use a smaller number of bits per every element. So for example, here, I just round every value to its nearest integer. And then you can see that, okay, I can spend 2 bits to save all these elements. And instead of using FB32. So this gives me 18x compression for compressing this. So basically quantization is the first solution. The other one would be a sparsification. And by sparsification, I mean, so for example, if you set a sparsity level, so here, let's say 50%, you want to sparsify your vector by 50%. This means that you remove half of your elements. By remove, you can think about putting them as a 0, or you can think about remove them and just save the rest of the element in a some sparse representation. So here, the main challenge is that you want to identify the least important elements, the elements that will have the least effect on your final loss, and then just remove them. So basically, a sparsity is another solution. And the other one is low rank approximation. And by low rank approximation, if you think about the weight metrics, as any kind of metrics that here, I assume that this is a square metrics. So basically, you should be able to approximate it with multiplication of 2 matrices. So one is D by K and the other one is K by D. And then K is much, much smaller than large D. So basically, if your original weight matrix has D squared parameter, then you can end up with something like 2 times dk parameters. And if K is small, then you can save a lot of, you can approximate with a lot smaller number of parameters. So these are some efficiency solutions that people know for a long time. And basically, what we are interested in is basically applying these kind of techniques on post-training. So basically, you can think about each of these methods as a method to compress your model, but you can compress your model and then retrain it. So basically, of course, by compressing your model, you introduce some level of error, but then if you retrain or if you train it from scratch, then you let your model to adjust itself and parameter by this change, and maybe you can compensate the error that you just introduced during the compression. But here, because the training aware schemes are quite expensive, you need to retrain, you need to do the full training, you need to do the backward forward pass and so on. Here we focus on post-training scheme. Okay. So yeah, let's start with the sparsity here. So here for sparsification, we consider sparsifying these linear layers in the LLMs. And these linear layers, you always have the weight matrix W, and then you also have an input matrix X, which is a set of usually a set of tokens that you feed into your network. And then basically you want to multiply these two metrics together. So this is the linear layer. And then, so you can apply some unstructured sparsity, which means that you go over the weight matrix. And then basically, because these weight metrics are the parameters of your model, so basically you go over them and just try to identify the least important one and just remove them. For example, here I removed 3 elements and then the last element from the first row and so on. So basically here you can do the unstructured sparsity. This means that your sparsity does not enforce any structure. Of course, this saves some memory for you. And you can also preserve the accuracy if you select, very carefully select your unimportant weights. But the problem here is that unstructured sparsity cannot give you any speed up. So basically you compress your model, you make it smaller, but you don't essentially get any speed up. Sometimes your model even gets slower, but it is hard to get a speed up with unstructured sparsity, especially these models, you cannot sparsify them something like 90%. You cannot sparsify them. Usually sparsifying this model more than 40 to 50% is quite hard.
Quick question. I guess on CPUs, you can perhaps get bigger speed ups, maybe because you have kind of a reduction in the arithmetic complexity. I guess it's more of a it's very hard to get speed up on a GPU specifically.
Yeah, exactly. Yeah. Okay, so this is very, very good point. Yeah, this is true, because this unstructured sparsity, actually the more precise word here is that a speed up here is really depends on the architecture that you are working with, and this is quite hard to get a speed up on GPUs. But yeah, here I assume that we do this inference on GPU. But yes, this is true that you can get some level of speed up on CPU. Yeah, this is correct. Okay, so moving from unstructured to a structured sparsity, so that there is very well known structured sparsity scheme which called 2 to 4, and then 2 to 4, if you think about it, so basically for every 4 elements, so for example here for every 4 element, you prune exactly 2 of them. So this is why it's called 2 to 4 structured sparsity. So you enforce some kind of a structure here, but the structure is like that. So you, for every 4 consequent elements, so you prune exactly 2 of them. So why this is important? Because this is developed by NVIDIA, and so basically you can save a bit less memory compared to higher level of unstructured sparsity. But the problem here is that because you need to enforce such a structure for a sparsity, you cannot preserve the accuracy anymore. So basically, because for example, here you think that, okay, if my 4 elements are the most important elements in my layer, then I have to remove 2 of them because I want to enforce such a structure. So basically, I may not preserve the accuracy. But you can get some level of speed up on the GPU with this tensor core and so on. Okay, and what we have introduced here is we calling it slicing. And by slicing, I mean, we want to slice, we want to remove some of the rows and columns from the weight matrix and of course from the corresponding input matrix. And so basically, you don't need to sparsify your model. So you get your model and just replace every single dense weight matrix with another dense but a smaller size matrix. So basically, this of course saves you memory. I will show you that this can preserve the accuracy. And of course, this can get a speed up because you don't need to do you don't need to involve any sparse matrix multiplication kernel at all. So you just run your dense matmul operation, but on smaller matrices. And this will be done. Okay, so this is, of course, cannot be done directly But this could be done if you apply some transformation, which I will call it Q during this talk, to the input and the weight matrix. Okay, let's talk about it. Okay, so first of all, the whole idea, if I want to give you the whole idea in one sentence, then I would say that, okay, so you can project your input matrix, input of every linear layer, into its principal components before matrix multiplication. So basically, if you think about your matrix as a matrix with a set of columns and set of rows, so then you want to remove some of these columns by projecting this matrix into its principal components. So basically, this means that we want to apply this transformation Q from the PCA over X. So basically, we do this for very simple algorithm. You can extract, you can get the input X, you apply PCA, you extract Q and multiply this to input matrix X, and then everything will be solved. So you end up with some smaller matrix, which you can multiply to a subset of your weight matrix. But let's go over it in more detail. So basically, you want to multiply this input matrix X to the weight matrix W. And what we want to do, we want to multiply the input to this Q. This Q is extract from PCA. But of course, if we want to keep the whole computation the same, we need also to multiply the inverse here, the inverse of the Q. So basically, you project this using Q matrix, but you need to inverse it back because you want to do at the end X times W. So basically, you need to also multiply it to its inverse. But then, if this Q is from the PCA, then you know that PCA has actually can, if you think about it intuitively, then PCA can accumulate the information of your input matrix to its first few columns. So basically, this is the description of the project into principal component. So basically, you have very few columns at the beginning, then which has the most important information, and you push all the information toward these columns. So basically, your last few columns have very least amount of information there. So basically, okay, so we know them. We know how to extract PCA here. And then basically the nice thing about this is that we can fuse the inverse matrix, this matrix Q transpose, into the weight matrix. So basically we can do this. So the projected matrix Q. And then basically what we know here is that these columns, this set of columns, are not that much important. They do not have that much information because we already fused the Q into X. And then if you think about matrix multiplication, these set of columns will always be multiplied to the last set of rows in the weight matrix. This new weight matrix, which we already fused the inverse into it. So what you can do, you can just remove these two parts. So basically, you can remove these columns from the inputs and also the corresponding rows from the weight matrix. That's it. You solve the problem. But here there is a very important challenge, is that you remember I just multiplied this Q into X, and this part is super expensive because X could be as large as this multiplication could be as expensive as the initial matrix multiplication. So this is not obvious how I can fuse this Q into X. So the main challenge here is that how we can remove this overhead of using this transformation matrix to the input matrix. The other part is easy because you can fuse the inverse to the weights. You can do it offline if by assuming that this Q is always the same among different data sets. I will go into the detail. Is it any question, something so far? Okay, so yeah.
Actually, quick question. Actually, what would Q look like? I mean, this is maybe just exposing how long I've not done linear algebra for, but basically assuming that what we get after applying Q is the principal component, which is like this kind of linear orthogonal set of vectors. Like, what does Q typically look like? Is it going to be the same across data sets? Why might that vary?
Sorry, I couldn't hear your question very well. Can you?
So you said that Q might vary across data sets.
Mm-hmm.
Is that the case? Q might look different for different data sets, basically.
I will go over it in the later slides. So basically, So this is one of the things that I want to show you, that actually Q is not quite different among different data sets. So this is the point.
Okay.
But I will go into the detail.
Okay.
But this is the general idea. And then we want to remove the overhead of multiplying these metrics into the input here. If you want to fix this challenge, then we should go over the architecture one more time. So basically, if you think about this transformer block, then you have a set of, so every LLM has a set of transformer block, and every transformer block has three main components. The first component is the attention module. And the attention module, so basically you feed the input into the three linear layers, so which you call it QKV, QProj, KProj, and VProj. And then basically, then the output will feed into another module, which is multi-head attention. If you don't know what is it, you can think about it as a nonlinear module. So you have some nonlinear multi-head attention module at the middle, and then you have another output linear layer. So this is the attention block. So basically your input will feed into this attention block, and then you have also the layer norm. And the layer norm, what does this module do? So basically you normalize your input. This means that you make it zero mean and unit standard deviation. And then also you multiply it to some scales that you already pre-trained during the pre-training step. So if you think about the layer norm, so you can write also the layer norm as the three parts. So one part is the mean subtraction, which you can already write it as a matrix multiplication or matrix transformation. So then you have the normalization. So basically you normalize the already subtracted mean input. And then you have also another linear transformation, which is a diagonal matrix that you multiply to it. So this is the layer norm module. And then of course, this is not how you write your layer norm in PyTorch, for example, or this is not how the way that you implement it in action, because these are some element-wise operation. You don't have to construct these matrices and then multiply them to the input. But here I want to give you the intuition that all these layers have some linear transformation at the beginning and at the end. And also, this is also true for the feed-forward network. So basically, for the feed-forward part, you again have the linear layer at the beginning, some activation function at the middle, and another linear transformation at the end. So if you think about all these layers, then you see that you have a set of layers with some linear transformation at the input and some linear transformation at their output. So the initial idea that we have here is basically for the layer norm, what we can do is we can fuse this linear operation into its adjacent linear operations. So basically, I have this linear transformation here, and I can fuse it into the weights of the next fully connected layer. And you can do the same for the other linear transformation together. So basically, this ends up with another network. So you can, of course, you can do it with the other parts of the network and fuse them into the adjacent linear layers, and you end up with a network that performs exactly the same. So basically, the output is exactly the same, but you have only RMS norm. You do not have any layer norm anymore, and you have only a single RMS norm operation at the middle of these different modules. So this is something that for every network you can come up with the equivalent network with only RMS norm. Okay, so why this is important? Why this important to fuse these stuffs and replace a layer norm with RMS norm? Because this RMS norm has very nice property. If you have an orthogonal matrix Q, orthogonal, so by orthogonal means that a matrix that every single column, their norm will be 1, and then every 2 columns will be orthogonal to each other. So the inner product of every 2 column will be 0. So for every orthogonal matrix Q, then you have this distributive property. So if you multiply this X to Q before RMS norm, then this is equivalent to multiplying the RMS norm of X to Q. So you now get some feeling why this is important, this transformation. Because right now, what I can do, I can fuse the Q, this transformation that I wanted to do in the previous linear layer. So basically, I can fuse the Q here, and then the inverse to this way. So basically, the Q and Q transpose here, because my Q from PCA is orthogonal, of course. And then I'm mostly sure that the output of the attention and the input of the MLP will be already transformed using the PCA that I wanted. And I can remove the whole overhead that we heard about. Does it make sense? Okay. Okay, so basically this is the second idea. And then basically the other idea is that you can apply it, of course, for the other models. But then the problem that you have is that you have also some shortcuts here. So you have some shortcuts. So basically here, the input of your model is already transformed by Q, because I already transformed the Q to the previous layer, of course. And then, so here, if you think about it, the output of the attention will be transformed by Q. And then the input, this shortcut, is already transformed by Q. So basically, you can sum over these two and feed it into the next layer. So you don't have to do anything else. But then this requires the assumption that this Q is the same for the whole model. So this is the Q that I exactly fused to the previous layer and the next layer and so on. But what we have seen is that this is not true assumption. So basically, you need to use different Q for different transformer blocks. So basically, you need a Q1 for the first, for example, here for the attention one, and then you need the other one, the Q2 for the MLP. And these are different because the inputs will be on the different space. So basically, the PCA will not project them exactly on the same subspace. So basically, you need applying different PCA and extracting different transformation matrices. So okay, so basically this enforces a new problem here, that because your input is already in Q1, and then the output of the attention will be on Q2. So basically you need to add another transformation on the shortcut, which is the Q1 transpose. So you need to multiply by Q1 transpose times Q2 matrix. And if you think about this matrix reverse the Q1 transformation and then apply the Q2 transformation. Okay, so this can solve the issue that we have with the shortcut rotation. But of course, this comes with the overhead of this other multiplication. But this is quite a small matrix. I will go into the detail, but this is very a small matrix because if you go from the large dimension to a small dimension, then the size of this matrix will be a small dimension squared will be the size of this matrix. But this is, of course, the number of parameters that you need to introduce here. Okay, so if you put all these parts together, then you can come up with the main idea of a SliceGPT. So basically, the main steps are quite simple. So you start from a pre-trained model. You transform it from the RMS norm net to an RMS norm network by fusing this linear operation. So this could be done offline once when you start with your pre-trained model. Then you extract this transformation matrix. And what we have seen here is that for every linear layer that you want to extract, you only need to extract it using a calibration set. So basically, we get some samples from the training set. I will show you the details. But you will extract these matrices, and then you apply the PCA over them using this calibration set. And then you will have a set of transformation matrix QI, I would say. And then you fuse this transformation into the adjacent weights. And then, of course, you fuse the embeddings and the head for the first and last transformations. Then you know that, okay, with this transformation, my input will be already small, has much less columns. So basically, then you can remove the last few columns based on the number of columns that you want to remove. And of course, it depends on your final accuracy that you want. So yeah, this is the whole idea of SliceGPT. And then, okay, do you have any questions, something here?
No questions from me. I think it's been incredibly well explained so far, so no questions from my side.
Okay. Yeah, perfect. That's it. So let's see how this will be performed in action. So, okay, first of all, we start to apply SliceGPT on both families of OPT and Llama models. The main difference, one of the main difference between Llama 2 architecture and OPT is that the MLP in the Llama 2 models, they have 3 different linear layers, but you can apply the same idea. Everything will be the same. You can apply the same on that MLP. Nothing will be changed. And but you apply it on 2 linear layers. So basically, for extracting this PCA, we extract samples from training set as a calibration set. We try with different calibration set with different data set, and I will show you the results. And basically, we compare it against this 2-to-4 sparsity with this sparse GPT, which is a state-of-the-art sparsity scheme, post-training sparsity scheme with a speed up. So this is the only sparsity scheme that you can get a speed up out of it.
Is this using NVIDIA's kind of blocked sparsity?
Yeah, so this is yes. Okay. So yeah, this
and that means you keep 2 weights of every 4 in the adjacent.
Exactly. Yeah. Okay.
So, one question which I'm sure you're going to address was just how many of the rows. I think I read maybe 25% is not used. Do you keep 75% of the rows, or maybe you like change this?
Yeah, this is exactly what I'm going to show here. Okay. So basically, these are the results. This is for the calibration set we use Wikitext2 training set. So this is generation perplexity, and if you're not familiar with it, so basically this is some kind of loss over the generation which your LLM want to predict the next token, and then basically this is on the Wikitext2 data set. So basically the lower is the better. So basically if you think about the dense model, then this means that we start from 125 million model to 66 billion, and you see that the perplexity will be decreasing. So the lower is the better. And then the same for the Llama model. And then basically we have this sparse GPT 2-to-4, which is actually, you see the gap between the dense and the sparse model here. And also we have a SliceGPT with different level of slicing. So here with 10% SliceGPT, this means that you remove the last 10% of the rows. So basically you remove the 10% of the parameters approximately. Or with 30%, this means that you remove 30% of your model parameters. So yeah, so we get in most of the cases up to 25%. We always better than this sparse GPT with 2 to 4. And then this is for the generation test. And the other kind of tests are the tests that are people known as zero-shot tests. These are some other data set which are mostly about question answering, some other tests, something related to some questions and so on. And again, here we apply, so basically here we use two different calibration sets. One is Wikitext2 as a calibration set, and the other one is Alpaca, which is another training set. And then basically we try with this OPT and Llama 2 families. And then also we try with this Phi2. This Phi2 is a small model, which is very well trained on a very high quality data. So basically this will be, so this is 2.8 billion parameter. And then basically we apply with different level of sparsity here, I could say. So from 20% to 30%. And what you can see here is that basically, first of all, Alpaca, it seems that this is a better calibration set. And then the other thing is, it seems that when you increase the size of the model, then you can compress them much easier. So you can see much smaller gap here compared to compared to smaller models. And this is usually because it seems that the larger model, you save more redundant information. And our scheme is somehow try to push the most of the useful information to the first few columns and just remove the rest. So this is my interpretation from these results. And then, so of course, here there are some gap between the slice one and the baseline model. And then we try to see, can we just quickly recover the accuracy by applying very few retraining steps. So basically, if we don't want to retrain the whole model and the whole data set, but just applying something like less than 1,000 steps, can we recover this accuracy? And the answer is yes. So basically, you can recover almost up to 99% of the accuracy with very few number of additional retraining steps. And if you think about it, this is a smaller model. So basically, the retraining will be much faster. And then I think the whole training here in the largest model takes less than 1 hour on a single GPU. This was I think the number that I remember. So yeah, so this means that okay, you can these models can quickly recover the accuracy from the retraining. And last, so basically also we can evaluate the end-to-end speed up. So basically here we have a measure of generating token. So basically average token per second. Okay, so basically, sorry, average per token inference time. So basically this means that how much time your model spent to generate a single token. And basically we try with two type of the GPUs. One is A100, which is very high-end GPU. And the other one is consumer-based GPU, which is RTX 6000. And then here, the most important part is basically we do not apply any code optimization on our code. So basically, this is the most naive PyTorch implementation without any optimization. So we simply get the Hugging Face code and then just change, apply our transformation. That's it. So you can think about this OPT 66 billion and 70 billion. They need 4 GPUs each. to run, and then these are the times that you need to spend to generate token on average. And then here is the multiplication of the number of GPUs to the time per GPU. So this is this multiplication. So this could show you usually, yeah, this could give you the sense how much I could allocate a GPU to generate these tasks. So this is, I would say, GPU token time. And then if you apply 25%, then you see that, okay, of course, because you remove 25% of your parameters, you immediately goes from 4 GPUs to 3 GPUs. This is true. The other one is that basically this GPU millisecond here is improved by something like 60%, we say. But the most interesting thing here is that without changing anything, because you do the same computation but on a smaller dense matrices, then you get very well a speed up here. And then you can get the same for the other type of GPUs. Here we go from 6 to 5 and from 7 to 5 GPUs and so on. So that's it. And if I want to conclude, so basically we discuss about the efficiency solution for the LLMs and the different sparsity schemes, and then slicing, how you can slice, what is the main challenge and how you can solve this. And also I showed you some results to how we can improve the LLM's efficiency by slicing them. So if you have any question, that's all from my side. If you have any question, I'm up to it.
Amazing. Yeah, well, first of all, let's give a big round of applause. That was a really, really interesting talk. Thank you so much for going through all of that. Okay, well, I can open it up to, again, I know I'm in a coffee shop, so again, hopefully the audio suppression of Google Meet is working okay. I certainly have some questions, but maybe first of all, I'll ask if anyone else in the room has any questions at all. Otherwise, I can dive in. Also, James, if you could take a look on, or if someone could take a look on YouTube, just in case there's any there. But I'll kick off then. So, yeah, like I wonder to what extent you think the kind of simple PCA approach, which just kind of obviously gets it into like a set of kind of linear orthogonal vectors. Is there a world in which there might be another matrix of the same size that's kind of missing the last 25% of rows or something that is even higher performing than the like first 75% of the principal component vectors? And do you think there's any kind of potential for learning using, like, you know, maybe distillation or something? You could like have the bigger model, you could do model distillation or something, look at the outputs and try to get a matrix that fully captures the behavior of the original matrix without using the kind of heuristic of PCA? Or do you think that there's nothing that, do you think there's nothing that's going to be better than PCA in terms of finding that smaller matrix?
First of all, what I have, okay, so first of all, PCA is really is a solution for L2 norm. So basically, if you think about the problem, then the optimization problem is L2 norm, and maybe you can say that, okay, this is not a great problem for this kind of thing, but if you go from L2 to other norms, then your problem immediately become harder, so you cannot solve it anymore.
Yeah.
One thing that we were very interested about is that basically, you know, if you know the literature of this linear algebra and the projection, then there is a large literature on random projection. So it says that if you come up with completely random metrics, then this does the same as PCA up to some constant that you can guarantee. And this is quite interesting that it seems that these random metrics that may be enough. But the problem that we had is that this is not true for the random orthogonal matrices.
Yeah.
Yeah, and you have seen that I use this property, this orthogonal property everywhere, because if you don't have this orthogonal property, then your RMS norm may not have this may not pass your transformation. But then you may come up with some other idea. I'm not sure, to be honest, but maybe this random direction could be one direction. Otherwise, I don't have any better solution on top of my head for this.
How do you think this compares to? So actually, the one thing I didn't fully follow. Sorry, was about the training. So sorry, did you show some results where you said that if you take the 75% and then you do a bit more training on top, you can improve the performance? Was that the case? Sorry to get. Would you mind kind of quickly going through that again? So I didn't fully follow. Basically, was the finding that then if you do some simple fine tuning, you can recover the lost performance? Was that the main takeaway?
This is good, but the thing is that you don't have to do this retraining. So basically, it really depends on the model, and then it depends also on your computational resources. So maybe you don't. Someone can afford such retraining, but someone
And so, were you able to like recover the full accuracy of the original model pretty much? What was the drop off after retraining?
So it was less than 1 to 2%, I would say.
Okay, so it's like less than 1 to 2%, and then without the retraining, what was it before that again? Sorry.
It also depends on the model, but it is, I think. I think I can go over the slides again.
Yeah, sorry, that was the one thing that I just missed.
So it depends on the slicity level. So basically, for example, for the largest llama, let me share my screen again.
Because I guess like the fact that it works in a somewhat one-shot basis, or kind of zero or offline basis.
Okay, so for example, here, if you compare the largest OPT and the largest llama model, of course, OPT has more redundant parameters. And then this is quite old model. And then you see that you have at most 0.3 perplexity jump. And then here, so you start from 0.3 up to, let's say, 1.
And then, but this is without fine tuning, right? This is just
this is without fine tuning, and this also without fine tuning. So basically, so this is on the zero shot test.
And then with fine tuning, it kind of improved. I'm just trying to make sense of the difference. I guess. Okay. So they just push up and get better, basically. I'll look at the paper and look at these numbers. So that's interesting, definitely. Well, Anvar's got a question.
In addition to measuring the perplexity after compressing the model, do you also measure the actual downstream task performance, like actually run the model with some inputs and measure the output, and like observe the output and compare that with the uncompressed model? And is that the same, or is there some noise or some artifacts introduced as part of because of like the sparsity?
Okay, so basically, that would be a very good question. So actually, I consider this zero shot test as what you just mentioned. So basically, so you have this generation task, which you want to predict the next token each time. But then these zero shot tasks are the tasks that your model have never seen before. And then these are something like some kind of question which sometimes try to make some mess with your model and so on. And basically, these are but we haven't done something by ourselves to this because what kind of data set you come up with is basically could be quite biased. So basically, and may not be that fair to compare against the other schemes. I remember there was some internal document classification data set, which was internal for Microsoft, and basically they tried this SliceGPT on top of the model for that data set, and they got much better result than almost all of what I have showed you. So, but we conclude that okay, the data set could be quite easy. So So this is what we have tried here, but of course trying on more data set could be much more interesting.
Yeah, but it's also interesting. I mean, yeah, it's a good like measuring the zero task performance is a good proxy for like just finding out if there's any noise or artifacts introduced as part of the sparsity. Yep. Thanks.
Another question on my side. I guess I was thinking about how complementary this slicing approach could be to other forms of compression, like pruning or quantization and so on. But I guess actually probably this is not that complementary to pruning, because effectively the matrix representation has become more densely informative on the left side. So pruning is less possible. Is that the case?
Yeah, I agree. So yeah, this is I think the most important question after this talk that I always asked by people, and then yeah, this is very quite important, and not for pruning, but maybe for quantization.
Yeah.
And
well, I can imagine quantization might be a little bit more like easier to combine. Maybe I'm wrong, but it feels like, because obviously then it's kind of done maybe more uniformly across the weights. But I guess pruning, I mean, if you are going to do any pruning, you would get the idea that you would be pruning anything that's more on the right-hand side that's part of the smaller components. But even then, like, why prune, and why not just slice off another row? Like, I guess it's kind of, you're kind of doing a form of pruning in a way. You're kind of pruning rows of a matrix to some extent, whereas quantization feels like it's a very nice way of doing structured pruning almost, I guess. You could almost see it as being this way, kind of. It's like restructuring the data and then doing very structured pruning on the edges of the matrix or something. And I guess you would ask, why would you combine this with unstructured pruning when you've now got this very nice structure? But I guess quantization makes more sense.
Yeah, so basically, yeah, actually, yeah, this is true. So basically, the quantization is usually much easier to compared to pruning. So we tried with pruning, I think, on top of a SliceGPT, and
yeah,
we use this unstructured.
You tried with unstructured pruning.
Yeah, with unstructured one, and it doesn't. Yeah,
were you just trying weight magnitude based pruning? Were you just doing it based on the magnitude of weights?
No. You have this sparse GPT, which is somehow second order method.
Okay. So it looks at the gradient of the actual input distributions and everything like this.
Yeah, Bayesian of the,
okay.
Yeah. But then
it needs inputs to calculate that, obviously.
Yeah.
Okay. Have you found that second order methods, well, I guess they are by and large, but is your experience that second order methods are generally much better than simple weight based methods?
Yeah. This is what they showed also in their paper. So basically, the magnitude pruning, you cannot go further than, I think, 10% or something, or even less. And
we had an interesting talk about magnitude-based pruning actually a couple of weeks ago, about the kind of fundamental sparsity of LLMs and stuff. But yeah, it definitely limited in terms of how far it can get. Are there any? Let me have a quick look. I don't think there's any questions on the YouTube, but any other questions inside the room at all? So we've got, thank you for the talk. Thanks, Dan, for staying this curious, and your questions are really what we're, okay, there we go. Awesome. I'm glad that people like my questions as well. But no other questions on the YouTube right now. Any other questions in the room before we wrap up at all? No. Okay, cool. Well, again, Saleh, it was really, really great to have you with us. Again, like, as I'm sure you're going to keep rolling out many more killer papers in the LLM space, and I'd love to have you back again in future.
Thank you. Thanks for the invitation. It was quite nice to talk with you. Yeah, and others.
It was amazing to have you. Again, let's give another big round of applause, everybody. Again, thanks for joining us, and yeah, thanks for joining everyone that was watching online as well. We'll see you in the next one. I forgot what we've got next week, but we've got something. We always got something lined up. Next week, we're going through teacher-student architecture for knowledge distillation, which is an interesting survey there. So anyway, have a good day, everybody. Thank you again, Saleh. Great to have you with us, and see you guys all again next week.
Thank you.
Bye.
Bye.